at the check your understanding on. So we're going to check our understanding. That is the weirdest writing ever. And that is on page 144 for your reference. So number 1 talks about how does drinking beer affect the level of alcohol in people's blood? I imagine it makes it go up. Just, I know. That's color me crazy, but that's probably what's going to happen. Anyhow, the legal limit for driving in all states is 0.08%. In a study of adult volunteers drank different numbers of cans of beer. 30 minutes later, a police officer measured their blood alcohol levels. We need to identify the explanatory and response variables. Okay. So what are we doing to them? Making them drink beer. Okay. So we're wanting to know, does the amount of beer that one drinks affect one's blood alcohol level? Yeah? So then our explanatory variable that should be what? It's got to be, and now if we're going to name it, it's always got to be, so I can't say beer. Right? That's not quantitative, right? It needs to be quantitative. So I'd say number of cans of beer, right? That's what we would put on our x-axis if we were going to be plotting this, right? So number of cans of beer. I did not write this, so I'm not just going to be talking about it. The alcohol percentage will be our response variable. Because that's how we're measuring it, right? It says the police officer is measuring their blood alcohol levels, which are being measured in percentages. No, because it's being, you're right. It'd be cool to take that into consideration. I think they're all being given the same beer. So all these beers would have the same alcohol percentage. I don't know why we're choosing it. So yeah, blood alcohol levels in percentages, right? If I could spell, that would be amazing. And we want to make sure that that's expressed in percentages. All right, fantastic. I think we answered that question. Let's do the next one. The National Student Loan Survey provides data on the amount of debt for recent college graduates, their current income, and how stressed they feel about college debt. A sociologist looks at the data with the goal of using the amount of debt and income to explain the stress by college debt. I usually read these questions twice, honestly. Like when I go through and take, and I do that just to keep myself sharp, I'll go through and take old AP exams. Weird. I usually wind up reading the question many times. I don't know if I'll ever, I mean, it has to be a pretty easy question for me not to read it twice. So I'm going to read it again. The amount of debt for their current income. And I don't know how they're measuring this. So these have to be quantitative, right? So income, great, right? Debt, great. I don't know if it could be both things. Income and debt. I guess they could subtract one from the other or something and come up with some sort of numeric value, right? But our explanatory variable would be income and debt. This one's not as good as the beer. And then our response variable would be our level of stress, right? I don't know how they're going to measure that. If they are, it needs to be, it needs to be some sort of a quantitative value that's put on stress. I'm sure that somebody has created a stress level indicator test that has how do you feel? Do you feel? Yeah, but that doesn't. That seems so subjective, right? My 10 stress is probably not the same 10 stress as the President of the United States. Yeah. I wonder if there's some physiological way to actually measure that. Anyway. Yes. Yeah, they could measure heart rate possibly and blood pressure while someone talks about their debt to see how stressed out they are about it. That'd be interesting. And that's great stuff that we'll talk about a lot when we get into our experimental design portion of the class, which is more logic and not much math. All right, let's move on to the next check your understanding. It is on page 149. Okay. We have a graph. If you look at it, I'm not going to draw it exactly. I'm not going to draw my scales. The picture is there for you, but I want to be able to point at stuff. So it looks kind of like that, right? So you've got a scatter plot. Looks like that. If I put this as an answer on an AP exam, I would get it wrong because I do not have a title or I have not labeled my axes as well. So that would be incorrect. But we're just talking about it. I'm just making a representation of the picture that we have in front of us. So let's describe the direction of this relationship and explain why it makes sense. So, number one, the direction. It looks positive, right? Direction is positive. Why do we say that it's positive? If we were to put it into context, and so now I need to actually read what this is. And the reason, so I could say generally, right, that for each increase in units in my x direction, it looks like we are consistently having an increase in units in our y direction, right? That definitely indicates that it's a positive relationship. But in AP Stat, we want to get fancy and actually state why it's a positive relationship in context. So the context of this is that so Stark's family arrived at Old Faithful after it had erupted. They wondered how long it would be until the next eruption. So here's the scatter plot. It plots the interval between consecutive eruptions of Old Faithful against the duration of the previous eruption for the month prior to their visit. Okay, so do we understand what's going on here? I had to think about it for a minute. Whenever I think about AP Stat, is that we have very contextual problems. And so when I am reading it and I want to interpret the context, I actually put myself in the position of the person having that particular experience. I really do that in my mind. I actually do. So I'm thinking, okay, what's going on? This graph, this is our duration. Our duration between eruptions, right? Is it called an eruption? Yes. And this is the length. Wait, I think I'm reading it wrong. Interval between duration. Sorry, this is the length of the eruption. I was doing it wrong. And this is the interval between eruptions. So it's saying that the longer the eruption lasts, the longer the interval between eruptions is. Right? That's what this thing is indicating. Fantastic. Awesome. All right, so if we were going to now explain this in context, we would say that I want to put it in context of units, right? No, we could just, so we could say as the length of eruptions increases. Yeah. The duration of interval. No, I don't want to use the word duration because it's down there. That's what's messed up about this, that they're both durations. The interval between eruptions increases. Fantastic, right? Anything weird about that? It's just kind of it's just interpreting a problem. All right. Hey, what form does the relationship take? So our form it looks, so in other words, does it look like the relationship is curved? Does it look like it's linear? It looks pretty linear, right? So the form is linear. It always bugs me when people say linear. And book mentions with two clusters, but I guess this idea is I guess we'll stay with two clusters. Mine isn't looking as clustered as your book is. And we're going to leave it at that because we're actually going to have a way of determining numerically whether these things are linear, quadratic, or exponential. We'll actually transform something that is exponential or quadratic, if the relationship is, in order to actually use least squares regression to make predictions, right? To come up with an equation for the line for that. So we'll leave it at this. We're going to get in much more detail with this. When we do transformations, it's kind of neat. You get to actually use logarithms for something useful other than solving equations. Actually, you get to see one of their main uses. It's transforming data. That is exponential. All right. How strong? It looks fairly strong. I would say the relationship is strong. And why is that? If I was to draw a line, if I was to really just, I mean, that's an estimation, right? We're not going to see too much of a difference, right? So, on average, the difference each point is away from the x or y value on that line is fairly small, right? You don't see much of a difference there. We could say the data doesn't deviate. Maybe it does not. And again, because I'm doing statistics, I'm going to cover myself and say for the most part. If I said it doesn't deviate from a linear pattern, I might be implying that the relationship is exactly linear, and that wouldn't be good. Are there any outliers? And now mine looks bad. There is one sitting like up there on your graph, and there's one sitting, I guess I got that one kind of right. There's one sitting over, there's one sitting here, and one sitting over here. And it's possible. We would have to check if they are indeed outliers. And what do they say about it? They say there are a few possible ones, but yeah, there's nothing that really sticks it way far out. Yeah, that's it. Yeah, there are a couple possible outliers. We'll actually be able to determine whether certain specific points are outliers by looking at the interquartile range of the y values, right? Because so it could be an outlier because it's sticking way high or way low in the y direction, or it could be an outlier because it's way low or way high in the x direction as well, right? So those are the two ways we can have an outlier. And lastly, what information do they need to predict when the next eruption will occur? Well, they need to know the previous eruption, right? This data that they have is good enough for them to predict. Okay? All right. Let's move on. I'm hoping to knock all these out today. So the next one is on page 153. And we have, where is the question? So we have 4 scatter plots. Unfortunately, I don't have the pictures to put them on this, so you have to look at your book to see. So A repeats the humanity plot. B shows the number of named tropical storms predicted. And C plots the healing rate in micrometers per hour for 2 front limbs with several newts. And D shows stock market performance in the consecutive year. For each graph, estimate the correlation R. And interpret this. Okay. So I would estimate for A, I would estimate that R is fairly close to 1. So maybe we would say it's an estimate, right? So I don't know, maybe 0.9, something like that. In order for it to be 1, I would actually have to have those dots lining up in an exactly linear pattern. Right, that's the only way that it could be exactly 1. So for B, it looks like a positive relationship, right? But not quite as good. So maybe I would estimate it at around 0.5. Which is what the book thinks too. So they think it should be around 0.5, right? Huh? Do you want to know technology-wise or what the actual formula is? So it is 1 minus n times x minus x bar divided by the standard deviation of x times y minus y bar, the mean of y, divided by the standard deviation of y, right? And you're doing that for each individual x value and each individual y value as well. It is written in your books. On the next page, 154. And you're adding them up. You're adding up all of those values. Yeah, that's the formula. So the formula for that is on 154. Technology-wise, you're going to have 2 sets of data. You absolutely need to have both all of your data for your explanatory variable and all of your data for your response variable. You're going to have those corresponding values, x and y values, in a table. Then you'll go to your calculator. You will go to stat. You'll do stat calculations. And there's a least squares regression, mx plus v. You can do the v plus mx as well. And it'll spit out both your slope, your y-intercept, your r value. It'll give you also an r squared value that we'll talk about a little bit later. But that r value will be in there in that calculation that your calculator will spit out. We're only estimating.
Oh, we're estimating.
Yeah, we're only estimating right now. Yeah. So it's that value is probably wrong, but it's likely to be close. So, C. This one's probably not good. Maybe 0.25. And then we also need to determine, look at that, the healing rate for the limb. We need to determine, is that a positive relationship or a negative relationship? For C, I mean, what would make sense? If I was to draw a line that came closest to all the points, right, that decreased on average the distance each point is from that line. You know what I'm saying? Would it make more sense to draw a line that has a negative slope or a line that has a positive slope? Think about it. If I draw a line that has a negative slope, I've got all of those points down there, 1, 15, and all that, right? I've got all those points in the lower left-hand side of that graph that are going to be so far away from that line. So far, right? But if I draw a line that has a positive slope, I will have much less, there will be a lot less points that are far away from the line that I would draw. Okay. It looks a lot like this. Let's see. Alright. So this is what I'm saying. Okay? If I draw my line, if I try to get it as close as I can, and I draw a line, I think maybe like that, maybe, right? But the problem is look at how far away this point is, and this point is, and this point is, right? I wind up with a lot of points that are very far away from the x and y values that I would have on that line. If I draw it like this, then on average, my x and y values of my data points aren't as far away from that line. Yeah? So I would say that the relationship is probably positive. That's how I would determine it. It's not very strong, for sure, right? I said approximately 0.25. The book, I think, said 0.3. Yeah. Okay. D. Last year's percent return, this year's percent return. That looks like there's almost no correlation, right? So I would give that a value very close to 0. But what we need to determine is, do we think that this relationship is the direction negative or positive? And it looks to be negative, right? It looks like it trends towards as my x value increases, my y values are decreasing, right? So I would say that it's negative. I would say it's probably fairly close to 0, which would be something like negative 0.1. I think it's probably, I don't know. That's probably about right. It's an estimate, though. We'll get actual real stuff going on here in a little bit. Yes. And that was 3.1. The only thing that they don't have in this 3.1 is, and that we haven't discussed a lot in detail up to this point, is the idea of correlation not implying causation. So it's very important that we're careful with this, right? Because I could make this graph right here. I could say ice cream sales is my explanatory variable. And my response variable could be boating deaths. And we would notice that definitely if I was to take this data, we would have a fairly strong positive linear relationship between ice cream sales and boating deaths. Does that mean that people are getting crazy with ice cream on boats and killing themselves and others? Probably not, right? There's something else going on, right, that's causing this relationship. You can have a really strong relationship, right? That actually means nothing. For instance, this one, right? What's really going on is that people don't eat ice cream in the winter, nor do they go out on their boats very much, right? However, as the temperature increases, ice cream sales likely increase, as do boating decks. That's the classic example. For correlation does not imply causation. This is probably, I mean, really, if you were to take this data, it would probably be very nice as far as like an R value that you would get. It just really doesn't mean anything. Cool? Hey, guys, thanks for checking your understanding before you wrecking your understanding.